Imagine traveling farther than any human being has ever traveled. You leave Earth behind, then the solar system, then the Milky Way. You cross enormous cosmic voids, past billions of galaxies, and continue toward the most distant light humanity has ever detected. Eventually, you reach what appears to be the edge of the observable universe. What would you find there? A gigantic wall? An endless black void? Or perhaps a boundary carrying the strangest warning imaginable? The universe ends here. But if a wall existed, what would be on the other side? If there were absolutely nothing beyond it, where would that nothing exist? And if the universe is infinite, how can something already infinite continue to expand? These questions sound simple until we try to answer them. Then, language, imagination, and even ordinary logic begin to fail us. Today, EXEPEL is traveling toward the possible edge of existence. But by the end of this journey, we may discover something unexpected. Perhaps the boundary we are searching for is not the boundary of the universe. Perhaps it is the boundary of the human mind. Before we begin, we must separate two ideas that are often confused: the observable universe and the entire universe. The universe is approximately 13.8 billion years old. Because light does not travel instantly, looking into space also means looking into the past. When we observe the sun, we see it as it was about 8 minutes ago. When we observe the Andromeda galaxy, we see light that began its journey roughly 2.5 million years ago. The oldest light we can directly observe has traveled for almost the entire history of the universe. So it might seem logical to assume that the observable universe has a radius of 13.8 billion light-years. But it does not. The most distant regions we can observe are now approximately 46 billion light-years away, making the observable universe about 92 billion light-years across. How can something 46 billion light-years away be visible in a universe only 13.8 billion years old? Because while that ancient light was traveling toward us, space itself continued to expand. The light kept moving in our direction, but the distance between us and its source grew enormously during the journey. This means the observable universe is much larger today than the distance the light originally traveled. Does this place Earth at the center of a gigantic cosmic sphere? Only from our point of view. Every observer stands at the center of their own observable universe. If an intelligent creature lived in a galaxy billions of light-years away, it would see a different cosmic sphere centered on itself. Imagine standing inside thick fog with a lamp. You can see only a limited distance in every direction. Your visible world appears to form a circle around you, but the landscape does not end where the fog hides it. Only your ability to see ends there. The cosmic horizon works in a similar way. It is not a wall, a cliff, or the physical edge of existence. It is a boundary in information. Beyond it are regions whose light has not had enough time to reach us. Some regions may remain hidden forever. Because cosmic expansion is accelerating, certain distant galaxies are receding in such a way that light emitted by them today may never reach Earth. The observable universe, therefore, has a limit. But does the entire universe have one? The most scientifically honest answer is also the most frustrating. We do not know. However, scientists are not simply guessing. We possess clues about the shape and geometry of space. One of the most important clues comes from the cosmic microwave background. This is ancient radiation, released when the universe was approximately 380,000 years old and had cooled enough for light to move freely. It is the oldest picture of the universe available to us. This radiation contains extremely small temperature variations. Those tiny patterns later became the seeds from which stars, galaxies, and enormous cosmic structures formed. They also allow scientists to test the geometry of space. On the largest scales, the universe could have one of three basic geometries. The first possibility is a positively curved universe. This can be compared to the surface of a sphere. A sphere has a limited surface area, but there is no edge where the surface suddenly stops. Imagine walking straight ahead across Earth. You could travel for years without finding the edge of the planet. If you continued in the same direction for long enough, you could eventually return to your starting point. Earth's surface is finite, yet it has no boundary. A closed universe could work in a similar way, although it would not be an ordinary sphere floating inside a larger room. Three-dimensional space itself would be curved. If such a universe were small enough, traveling continuously in one direction could theoretically bring you back from the opposite direction. You might look far enough into space and see ancient images of your own galaxy. The second possibility is negative curvature. Such space is often compared to the shape of a saddle. Parallel paths can move farther apart, and the geometry may continue forever. The third possibility is flat space. In flat geometry, parallel lines remain parallel, and the angles of a sufficiently large triangle add up to 180 degrees. This is the familiar geometry we usually learn at school. Measurements from the Planck mission and other cosmological observations show that the visible universe is extremely close to spatially flat. At first, this appears to solve the mystery. If space is flat, perhaps it must be infinite. But that conclusion is not guaranteed. Flat space can be infinite, yet certain possible topologies would allow it to be finite without possessing a conventional edge. Consider a video game world in which a character walking off the right side of the map reappears on the left. Walking through the top might return the character from the bottom. The map has a limited area, but the character never encounters a wall. The world is finite and still has no accessible edge. Three-dimensional space could theoretically possess an even stranger connected structure. We do not currently have evidence proving that it does, but measurements of flatness alone cannot completely eliminate the possibility. There is another problem. A tiny region of an enormous curved surface looks flat. Stand in a large field and look at the ground. You will not immediately see Earth's curvature. The planet appears flat because the area visible to you is extremely small compared with Earth's total size. The same may be true of the cosmos. Our observable universe may be only a tiny region of a vastly larger curved universe. If the curvature appears only across distances much greater than 92 billion light-years, our instruments may be unable to detect it. So the universe could be infinite. It could also be finite, but unimaginably larger than the region we can observe. Some inflationary models suggest that the entire universe must be at least enormously larger than our observable region. Depending on the model, everything visible to us could represent only a microscopic fraction of the total cosmos. This leads to a disturbing realization. Every galaxy humanity has photographed, every black hole we have discovered, every star that has ever shone in our sky, and every apparently empty cosmic void may belong to only the smallest visible patch of reality. But what would an infinite universe actually mean? Infinity is not merely an extremely large number. No matter how many zeros we add, we never reach infinity. If space truly continues forever, and matter is distributed in roughly similar ways across it, then there could be infinitely many galaxies, stars, and planets. And this produces one of the strangest possible consequences. Within any limited region, particles can be arranged in an enormous but possibly finite number of meaningful configurations. If an infinite universe contains infinitely many such regions, configurations may eventually repeat. Somewhere, at an incomprehensible distance, there might be a galaxy resembling the Milky Way, a star resembling the Sun, and a planet resembling Earth. There could even be someone resembling you, listening to these exact words. Farther away, there might be another version in which you stopped the video a few seconds ago, and another in which life on Earth developed completely differently. This is not an observed fact, and scientists have not discovered a duplicate Earth. It is a speculative consequence produced by combining infinity with particular assumptions about matter and cosmic uniformity. It may also be impossible to test, because any such duplicate could lie forever beyond our cosmic horizon. Now we arrive at an even more confusing question. If the universe is expanding, what is it expanding into? We instinctively imagine an explosion. We picture matter flying outward from a central point into an enormous empty space. But the Big Bang was not an ordinary explosion inside a pre-existing cosmic room. According to modern cosmology, space itself expanded. Galaxies are not, simply racing through empty space from one central explosion site. On sufficiently large scales, the distances between galaxies increase because the structure of space changes. A common comparison is rising dough filled with raisins. As the dough expands, every raisin sees other raisins moving farther away. No raisin occupies the unique center of expansion inside the dough. But this analogy has a limitation. The dough expands into the surrounding kitchen. The universe, according to general relativity, does not require an external room. Asking what the universe expands into may be like asking what lies north of the North Pole. The question sounds reasonable, but it may depend on a direction that no longer exists at that point. The universe may not have an outside. If the universe is infinite today, some models indicate that it may have been infinite even in its earliest state. It would not have started as one tiny point sitting inside darkness. Instead, every region of an already infinite space would have been much hotter, denser, and closer together. When cosmologists say the early universe was extremely small, they often refer to the region that later became our observable universe, not necessarily the totality of all existence. Shortly after the beginning of the hot Big Bang phase, the universe may have experienced inflation, an extraordinarily rapid expansion of space. Inflation helps explain why distant parts of the observable universe have nearly the same temperature and why space appears so flat. But inflation also creates new mysteries. Some models suggest inflation may continue eternally in distant regions, producing countless expanding cosmic domains. This idea is sometimes called eternal inflation and is connected to certain versions of the multiverse. However, it remains theoretical. We do not yet possess direct observational proof that other universes exist. Even the future of our own visible region remains uncertain. For decades, the standard cosmological model has treated dark energy as a constant property of space. Dark energy is the name given to whatever is causing cosmic expansion to accelerate. If dark energy remains constant, the universe will probably continue expanding forever. Distant galaxies will disappear beyond our horizon. Star formation will eventually end. Existing stars will burn out, and the cosmos will move toward an increasingly cold, dark, and isolated future, often called the Big Freeze. But recent results have complicated that picture. In 2025, observations from the Dark Energy Spectroscopic Instrument, known as DESI, strengthened intriguing hints that dark energy may change over cosmic time. The evidence has not yet reached the level required to declare a discovery. The standard cosmological model remains extremely successful. But if dark energy is truly evolving, predictions about the universe's future may need to be rewritten. Expansion could change its behavior. Possibilities once considered unlikely might need to be examined again. The most important truth is that science has not yet delivered a final answer. We know the observable universe is finite. We know its present diameter is approximately 92 billion light-years. We know the visible cosmic horizon is not a physical wall. We know large-scale measurements are consistent with space being extremely close to flat. But we do not know whether the entire universe is finite or infinite. We do not know whether its full geometry matches the geometry of the region we can observe. And we do not know whether the word outside has any meaning when applied to the universe itself. Perhaps the universe continues forever. Perhaps it curves back into itself. Perhaps it is finite but has no edge. Or perhaps our observable cosmos is only one domain inside a reality far greater and stranger than anything the human mind evolved to understand. And that may be the deepest mystery of all. The human brain developed to survive on the African landscape, find food, recognize danger, and cooperate with other humans. It was never designed specifically to imagine curved three-dimensional space, cosmic horizons, or actual infinity. Yet this small biological organ is attempting to understand the shape of all existence. Maybe we have not found the boundary of the universe because it lies beyond every telescope we could ever build. Or maybe, while searching for the edge of space, we have quietly reached the edge of human intuition. So, what do you think? Is the universe infinite? Is it finite but without an edge? And if you could travel forever in one direction, would you discover new galaxies without end, return to the place where you started, or enter a region from which no signal could ever return? Share your answer in the comments, and if you want to continue exploring the greatest mysteries of science with EXEPEL, subscribe to the channel. Because the universe may or may not have a boundary, but every great discovery begins when someone refuses to place a boundary around the questions we are allowed to ask.